All right, next I wanted to look at how we can deal with the time-dependent part of the Schrodinger equation for a free particle, and also in general, what are we doing about the time dependence of the on the wave function, and the fact that this is a system that is a traveling wave that's evolving in time. And so we've seen before that for a traveling wave evolving in time, we could have something like y of x and t equals a times the sine of omega t plus or minus kx, where the minus sign would indicate motion to the right, and the plus sign would indicate motion of the traveling wave to the left. But we looked at solutions that look more like this, which were solutions to what we call the time-independent Schrodinger equation. And we see here the k value, but it doesn't look so much like a traveling wave because we don't have the time part in there. And so why are we able to ignore that? And what is the more general form for this solution? Well, that's what I want to get into here. Here is our equation that we've been using, our one-dimensional Schrodinger equation solution. And we also introduced the idea that we can have an operator, p op, that acts on our wave function in such a manner that p op times psi equals our momentum times psi back again. And so we've done this before, where we've used this momentum operator on the psi function, and what we've ended up with then, by taking the derivative with respect to x, is a momentum function times psi back again. Okay? But there's also an energy operator if we're dealing with a time-dependent function. And so for this problem, let's just assume that our total wave function can be written as a product of an x part of the wave function multiplied by a time part of the wave function. You might say, well, isn't that kind of a restrictive solution? To say that you can separate x and t. If I look at this equation here, I don't see any way to separate this into something that just involves x times something that just involves t. And yet you can if you write it in the complex exponential form, because a sine or cosine function, you could write this as plus b times the cosine of omega t plus or minus kx. That'd be a more complete solution. But we could rewrite this as some other a times e to the I times omega t minus kx plus or minus plus b prime e to the I times omega t plus kx. And so that can be shown to be equivalent to these two solutions. But we can rewrite this expression as a product of two functions. So this looks like a prime e to the I omega t times e to the minus I kx. So we can see here that by writing a solution like this, that is a sine function in terms of complex exponentials, which has the exact same information content in it, we are in fact able to use that to write our wave function as a product of something that only involves x and something that only involves time. And the reason why that's possible is that the exponents add. Okay? And so by writing this as the e to the omega t minus kx power, we can break that up into two different factors when they have the same number that's being raised to these different powers. You just add the exponents. Okay? And so let's do that then with the Schrodinger wave function and see where it gets us. And let's also introduce this new idea that instead of having an energy that is a constant value, we could write the energy in terms of an operation on our wave function. Okay, so if we go back to this equation, we've got minus h bar squared over 2m partial squared of psi x psi t respect to x squared, plus in general we'd have u of psi x psi t, like that. Would equal E. But here, let's write, instead of E, let's write the energy operator acting on the wave function. So this is going to be I h bar partial with respect to t of psi x psi t. Okay. And so this is a more general form then for the Schrodinger equation. And what I want to demonstrate here is that if we're dealing with something in which the energy is a constant, the time dependencies are going to cancel out. So let's see how that would work here. First of all, I can rewrite this first expression because psi t doesn't depend on x, so you can just consider it to be constant. So this is just minus h bar squared over 2m partial squared of psi x with respect to x squared times psi of t. So psi of t is over there as a separate factor. Plus u of psi x psi t equals, and then over here, it's only the psi t part that is going to get a differentiated, and the psi x part will stay constant because this is a partial derivative with respect to t. So this is going to be psi x times I h bar partial of psi t with respect to t. Okay, so now what I'm going to do, and this is similar to what I did with separation of variables for the three-dimensional particle in box, is I'm going to divide both sides of the equation through by psi x psi t. I'll do that here, psi x psi t. And here, psi x psi t. And so you'll notice then on this side, the psi t's are going to cancel for that first term. For the second term, the psi x's and the psi t's are going to cancel. And for the third term, the psi x's are going to cancel. Okay, now for the moment, let's just say this is a free particle. We'll set u equal to 0. And we'll see how to generalize this if u is not equal to 0 later. So what we've got then is minus h bar squared over 2m. And now this is a total derivative because it's only acting on psi x. So I can write this as d squared psi x dx squared. And then this is all divided by psi x is equal to I h bar partial of psi t with respect. Now this is a total derivative with respect to psi t because psi t only depends on time. And then that's all divided by psi t. Okay, so this is what it reduces to. So we've got something on the left that's only a function of x. Got something on the right that's only a function of t. And so the only way that these two things can be equal to each other, since this is only a function of time and this is only a function of x, is if they're both equal to a constant. And let's call that constant the energy of the system. Okay? And because that's what it turns out to be. So this is the constant. But it turns out that the physical description of what that constant represents is the energy of the system. And so if I rewrite this first equation and set it equal to the same constant as I have written for the second equation, what I end up getting for the first equation is minus h bar squared over 2m d squared psi dx squared equals e psi. Or if we had a u in there, it would be plus u of psi equals e of psi. So that would be true in general. And so this is just what we had before. Even if u is not equal to 0, we could write this as plus u psi equals e psi. Okay, and so this is just the solution to our x part of the wave function. And so this is what gave rise to our solutions before for free particle when u is equal to 0 that looked like psi is equal to a e to the I kx plus b e to the minus I kx. Because what we were solving here was just the part of the equation that involved the x part of the x dependence on psi. But now, let's go a little farther with this, and let's look at how the time dependence is going to look. So we know what the x dependence is going to look like. That just involves the separation of variables here of our Schrodinger equation that involves the x part of the wave function. But if we look at I h bar d psi t dt equals e psi t, then we need to solve that first order differential equation. So how do we do that? Well, we can do separation of variables here. And this is separable first order differential equation. So we can write this as d psi over psi of t equals e over I h bar times dt. Integrate this from some initial value for psi at time equals 0 to some final value of psi that's a function of time. Okay, and so I'll call this initial psi some constant a. And so then we can rewrite this then as the log of psi minus the log of a equals, and then here we have e over I h bar. If I multiply numerator and denominator by I, then this becomes minus e over IE over h bar. And then that would be multiplied by the time, 0 to t. Okay, so I can rewrite this on the right-hand side as minus I e t over h bar. And so then I can do the difference in the logs and exponentiate both sides of the equation. That gives me psi is equal to a e to the minus I et over h bar. Okay, and so we can think this would be some a prime if we want. So that's the time part of this function. So we had an x part of the function that looked like e to the ikx. And here is the time part that looks like e to the minus iet over h bar. So if we put those together, what we get then, and let's do this, for example, for the let's do it for the particle in a box. What we saw before is that psi of x is equal to square root of 2 over L times the sine of n pi x over L. And so now we have psi of t is equal to some other constant a times e to the minus I e t over h bar. Then we'd have psi total would equal root 2 over L sine n pi x over L times e to the times a, so I'll call this a prime here for some new constant, e to the minus I e t over h bar. So this then becomes the total wave function for the particle in a box, which means that the wave function is fluctuating back and forth like this with a certain frequency. That frequency can be given by the fact that h bar omega is equal to Planck's constant times the frequency, which is equal to e. So therefore omega is equal to e over h bar. And so this could also be written a prime sine n pi x over L e to the minus I omega t. And if you write it this way, then our solution for the free particle would look like this. We have psi of x, say, is equal to some a e to the I kx b e to the minus I kx. So then psi of x, psi of t would be equal to a prime e to the I kx minus omega t, or minus e t over h bar, plus b prime e to the minus I times kx minus et over h bar. This would be plus, because this is a minus, but I'm propagating the minus to the inside. So this looks like kx plus minus omega t. This looks like kx plus omega t. Okay, so those are the equations then for a traveling wave. Okay, but in problems where it's there's no change in the system over time, this part of the function that has to do with time is going to cancel out for any of the calculations that we're going to do. And so that leaves this part of the function as being the part that we would use for an energy that didn't change with time. Okay, so let's go back to this expression for the particle in a box, and let's find the, with this being our psi total, let's find the average value for the momentum, P average, for a particle in a box. P average then is going to be the integral of psi star. We've done this problem before, so check your notes on this if this doesn't look familiar to you. Times P op times psi dx. This is for a particle in a box. This is the average momentum of an electron in the particle in a box. And so that's going to look like the integral of psi star. That's going to be this expression here with a change in sign on the imaginary part. So that's going to look like A prime sine n pi x over L times e to the plus I et over h bar times p op, which is I h bar d by dx of psi back again. So that's going to be the sine of n pi x over L times e to the minus I et over h bar. That would be dx. Okay, so we can see then that because differentiation with respect to x doesn't affect something that is a function of time, this can be pulled out and combined with this, and the two cancel out and give us 1. Okay, so what is left here then, this should have an a prime in it also, is that this is just going to be the integral of a prime squared times the sine squared of n pi x over L dx from 0. I'm sorry, this is the derivative of this expression with respect to x. So that's the sine of n pi x over L times the derivative of the sine function inside of this expression is going to be the cosine of n pi x over L dx with an extra factor of n pi over L outside. Okay, and so this expression then, we were able to show before is equal to 0. Okay, so when we take the sine and we multiply that by the cosine function, what we end up getting over a symmetric interval is just 0. And that's something that I did in our previous lecture. But what I wanted to show here is that the reason why we could just deal with the x part of the wave function is that the time part is going to cancel out when you do psi star psi. Because what that gives you is something that involves the change in the sign on the complex exponential part, so that the complex exponential part just drops out of this expression and leaves us with something that is just a function of x. Okay, and so it's not some magical thing then that I'm writing the equation for a traveling wave like this. All this is representing is this is part of the total solution that is relevant in the steady state, where the steady state is where the system has found equilibrium and is no longer a function of time. So it's like, for example, an RC circuit. In an RC circuit, you've got some charge that is building as a function of time on the capacitor in an RC circuit, and eventually it grows until it reaches equilibrium. When it's at some maximum value, then we say that the system's in equilibrium and it's no longer in the charging part of its its cycle. It's not time dependent, in other words. And so when you're in the steady state, then that means that you could have, say, a beam of electrons that's being emitted at a steady rate, and then maybe there's a barrier or something, but then you just let all the transients in the system die down, and you end up with a steady state solution that's independent of time. If it's independent of time, then the time part of any of the calculations that you might want to do are going to go to zero. Okay, so with that idea in mind, let's see what having a constant energy does to the variance in E, let's say, for any particular problem where we have a constant E. Okay, so for example, we might be dealing with a particle in a box, or this could just be an electron that has a constant energy as a free particle that's moving, say, from left to right. Okay? Now, if it's got a constant energy, then we should be able to find the variance in E, and that variance in E should be equal to zero. From the uncertainty principle, remember that you have delta E delta T is equal to zero. And so with a system that has an absolutely constant energy that doesn't fluctuate, that means that the uncertainty principle is going to tell us that delta E is equal to zero. Now, how would we prove that? Well, let's say that if it has a constant energy, its variance squared, that's like your delta E in this case, going to be your variance, is going to be the variance on the average of the squares minus the variance of the average squared. Okay, so that's what delta E is going to be proportional to here for something that has a, actually be the square root of this. Square root of the variance squared be equal to that. And so let's see what the variance would be for the square of the average. Well, E average, that's going to be E average squared. Now, how do we write E average? Well, we can write that as the integral of psi star times E op times psi dx. Okay, so this is the way that we calculate the average value for a function. Remember, we did this for x bar too. We said that x bar, the average position for a particle in a box, would be the integral of psi star times x times psi dx. And we got for that from 0 to a, when we did this integral before, we got that it was equal to the midpoint of the box. Okay, and so this is true then for the average momentum. That's just the integral of psi star times p op psi dx. That's the one we just did, where this ends up being integral of psi times minus I h bar d by dx of psi dx. That is equal to 0 for the average momentum. So what about for the average energy? Well, it's just going to be this quantity squared. Right? So that would be the average squared. That would be this one here. Okay, so let's do that calculation. This is going to be the integral of psi star times I h bar times d psi dt times dx. And so to find this expression then, we need to go back and see, well, what is psi star? Well, psi star for our, say our particle in a box is going to have an x component, so that's going to look like the sine of n pi x over L times e to the plus I e t over h bar. And then psi, so that'll go in here. Times I h bar d psi dt. Okay, so we have an I h bar, and then when we take the derivative of this psi with respect to t, what we end up getting is all of this back again times the derivative of the inner function, which is going to be minus I e over h bar. And then that's going to be times the sine of n pi x over L times e to the minus I e t over h bar. We're integrating this over all x's. We see again that the time part cancels. And so what we end up getting here is just the integral from 0 to a of the sine squared of n pi x over L. And this should be times an a squared value out here. The h bars are going to cancel. I times I is minus 1 times minus 1 is just plus 1. So that's just e. So we end up then with just e times the sine squared of n pi x over L dx times our amplitude factor, which is going to be 2 over L, because a was equal to square root of 2 over L. And so then we have an a squared here. So that'll be 2 over L. Integrate this from 0. I guess we should be integrating this from 0 to L. Let's see, from 0 to a. Calling L the length of the box. So then this is just going to give us L over 2, or this is just the same thing as e times the integral of psi star psi dx, which is just 1, because we know that the integral of this over all space is just 1. We're integrating from 0 to L, and the particle has to be somewhere in the box. So in other words, what we end up with when we take the average value of E is basically what we're getting is just E, because that's all it is. It's never anything different from that. So the average value for E has to be E, because it's that way forever. And so that may seem like kind of a obvious thing, but when we write it this way, this integrates out to L over 2, this is 2 over L. So all we're left with then is just E. So the average value of E squared is just equal to E squared. Okay, so that's this one. Now let's do the same thing, but let's do it now for the sigma squared average part. The sigma squared average part is going to be equal to, well, E squared, and then we're going to take the average of that. Okay, so it's going to look like that. So that means that we're going to have to write this as psi star E op squared times psi dx. Okay, so does that mean if E op is equal to I h bar partial with respect to t, and what's E op squared? Well, do I just square this whole thing? No. What I do is I apply the operation twice. So E op squared is equal to E op operating, because that's what energy operators do, is they operate on themselves. And so what we need to do here then is operate on psi twice. So this is going to be the integral then of psi star times I h bar partial with respect to time of psi x psi t. And so it's only going to operate on the psi t part, right? And so what that's going to give us then is just going to be, and then you have to do this twice. This is I h bar partial with respect to time of psi t psi x. So I times I is minus 1. When we take the partial derivative of this with respect to time on psi t, what you end up getting, just like we did before, was psi star times I is I squared times h bar squared, and then we the partial with respect to time, so that's going to be E times psi x psi t back again times dx. This is, it's going to be I h bar squared partial with respect to time, because we've got to do it a second time. But when we've done it the second time, we've just pulled out the IH bars, and what we end up getting here is the partial with respect to time of the energy part of this. That's going to give us E over h bar minus E over h bar times psi back again times dx. And we have to take the partial of that one more time, sorry. So this is psi star. This was I squared h bar squared, and then we do one more time, partial with respect to time of this function here, and then that's going to pull out another E over h bar that's gonna, I squared's gonna give us minus 1. We have I, oh, there's another I, so that's I cubed, sorry. I cubed. And then this is I e, that's E psi over h bar, so that's gonna give us then just the integral of psi star times E squared psi dx. A little bit of algebra in there. But when we apply this operation to psi t twice, we end up getting psi t back again times psi x. So that's just our original psi. But each time that we operate on psi, we get the energy times psi back again. So that gives us a factor of e squared. So that e squared can be pulled outside, and that gives us the integral of psi star psi dx. But this integral over all space of just psi star psi is just equal to 1. So it's equal to e squared. Okay, so that's e squared average is e squared. But e average squared is also e squared. And so delta E is equal to the square root of E squared average minus E average squared. That's just equal to the square root of E squared minus E squared, which is 0. So basically what we've shown with this fairly long calculation here, first to get the E squared average, and then over here to get the E average squared, is that we're just getting the same thing both ways. And so is it just another way of saying that this system doesn't change its energy ever? If it doesn't ever change its energy, then is it violating the uncertainty principle to say that I know the energy perfectly? The answer is no, as long as delta t is infinity. So if delta E is 0, then that doesn't violate the uncertainty principle by knowing the energy exactly, as long as I can say that for all time, the energy is known to be that value. And so that means that delta t is infinity, and so that allows then for this to still satisfy the uncertainty principle of delta E delta t equaling h bar over 2.